Okay, I'm Rick Stevens. I got volunteered to give this keynote talk, I guess. So I'm going to talk about AI for science, which is the new kind of initiative concept that the DOE labs and DOE headquarters are working on. But first I'm going to ask you a question. Can Google search prove that we've been visited by time travelers from the future? How many people believe that's true? That Google can prove this, if it was true? If it was true, of course, well, you should read this article. It's a kind of a fun article. It looks for, if you query Google and look for what amounts to historical discontinuities, then the argument was that we were visited by time travelers. So I was asked to talk about the future, what we're thinking in the future. So I'm going to start by giving you three Fiveyear kind of vignettes, although this morning I was reading an article by the Harvard Business Review saying that for strategic planning you should not choose date targets that end in 0 or 5. That just shows a mental crutch. So think of these as prime numbers. I mean 5 is of course a prime number, but think of these as other prime numbers besides 5. Okay, so in 5 years out, what's the landscape going to look like? Well, so Aurora and Frontier are going to be running well, large number of applications, simulation, people are going to be doing machine learning on that. We're going to be making a lot of progress on integrating machine learning into applications that are trying to do things like search and design. And this will affect materials, drugs, bioengineering, manufacturing processes, and so on. As a side effect, other story I was reading this morning, I was up early, is a Chicago 3D printing company has printed, they just announced it, the first mini human heart, complete with ventricles, valves, and so on. Very cool. So Google that if you're bored of my talk. We'll have U.S. national initiatives running in AI and quantum computing. Of course, the quantum one is launching right now. Hopefully, Congress comes back and passes a budget. AI one is also being planned, but 5 years from now, these things aren't running. There'll be a broad progress in applications in AI and science, and I think these will impact energy and biomedical applications quite deeply. We'll have test beds for quantum and neuromorphic at some level, maybe in partnership with various companies. And there'll be software stacks people will be tinkering with how do we integrate things like quantum and classical together. I mean, it's already starting to happen, but there'll be more progress. So this is kind of what we expect in the next few years. 10 years out, I gave a version of this talk at Oak Ridge last week, so I put Oak Ridge in here too. But Argonne and Oak Ridge, we have deployed some kind of 100 exaOP machines. These are probably going to be hybrids that have a mixture of compute devices, including AI accelerators. We don't know exactly what they'll look like. But the driving application for that kind of our target architecture is going to be what we'll call AI for science, which is this quasi-undefined thing, which I'll talk about a little bit later. But I would say that simulations in this time frame, 10 years from now, are going to be essentially all managed by AI. Just like biology will be done by people sitting in coffee shops writing Python code that will execute in the robots in the BioCloud, running simulations will be done the same way. You write metacode to manage the simulations. We'll be thinking about ZetaOP machines, although it's not clear how we're going to account for the quantum and AI and neuromorphic components of these systems. So this notion of flops is going to be broken, but we'll have a LIMPAC Q benchmark. And what it actually means will be hotly debated, just like it still is about what LIMPAC means. AI will be used for managing systems, augmenting programming environments, drive performance optimization. We won't do dumb auto-tuning, we'll do smart auto-tuning, of course. And we're going to have the ability to passively analyze data sets. So storage devices won't be static, just store the bits. If you're going to write the bits out, you might as well do something with them in parallel with them sitting there, right? So this passive analysis of data, or maybe passive-aggressive analysis of data, where the storage system tries to figure out the patterns in the data spontaneously and ask you, well, I found something if you care. It's kind of like, grad students. Integrating machine learning and symbolic computing is going to be the long-term challenge, and it's going to be going slow even 10 years out from now, right? Quantum computers, I wrote this probably when I was more optimistic on quantum, but maybe 10 years out we'll be at 1 million qubits, but it still won't be enough to actually do real problems. But we'll have languages that can speak quantum, like Python 4. That's a Python joke if you know what Python 2. God, this is a really dead audience this morning. Come on, guys. Python joke. Python 4. Tell me how possible that is. That's not totally impossible, right? Okay. Julia Q, that'll be the proper version, right? And Fortran Q, because we'll still be supporting Fortran, but we'll have to use it for programming quantum machines. Of course, somebody asked a question about partnering. It'll be the normal way for US agencies and countries to do business, because we will not have enough money to do it otherwise. And if you go out 15 years out, Elon Musk is finally getting to Mars, okay? And he gave up on stainless steel, so it's white colored now. Another joke. It's still a dead audience. All right. Non-Von computing elements in this time frame are going to be the dominant thing, and that will blow everybody's mind, right? So that I think is, and how we will estimate compute cost and do development on these things will be a challenge. Storage systems will be replaced by in situ AI. You will not write data out to a storage system. You'll hand it off to an AI that will either learn a model and throw the data away, and when you ask for the data back, it'll just tell you what the data was. I can talk more about how that works. But what you want is the system to automatically come up with multi-level abstractions of your data. And that's something that we don't exactly know how to do, but by then we should be able to figure out how to do that. And what I mean by that is from reproducing the raw bits to giving you back some high-level function that learns, that captures the distribution on the data. Nearly everything that collects data will have some intelligence in it. So I think IoT is kind of the wrong concept because it talks about the internet. We don't actually care. It's really like the intelligence of things or something like that, right? Quantum computers that use distributed entanglement might actually be functioning by then, and IBM will be profitable in quantum computing at this point. That's for David. A major use of simulation to augment training data sets, that's what the HPC traditional business is going to be used for, is basically creating data sets that we can't collect from the real world. And we're already doing this in rare events in traffic simulations and so on, where the tail distribution is where we care about, rare, bizarre accidents, which of course we don't actually have real road data for that. Finally, there'll be a lot of foundational work. Okay, so that's my kind of arc, and you can argue with me if you like. I'm going to give you an update on what we're doing in the DOE space. So we have this initiative that we've launched called AI for Science. And one of the questions is this really an AI initiative, or is it really a roadmap for post-exascale computing, right? Or is it both of these things? So we are one day away from the 3rd town hall that'll be at Berkeley starting tomorrow. But there's 4 town halls, Argonne, Oak Ridge, Berkeley, and Washington, D.C., that have gathered about 1,000 people to grind through applications, software ideas, algorithms, integration with sensors, and so on to figure out what opportunities exist in this space. And this is very similar to what we did in 2007 that ultimately launched the exascale program. Okay? So that's the trajectory that we're on. If you missed the one at Argonne, this is what the picture was like. It was me up there talking. There's a zoom on me so you can see me more. But what we were doing was we're talking about, AI is transforming our regular life, but it hasn't yet transformed our scientific and engineering lives, but it will. And what do we need to do to make that happen in a way that we want? So what are the organizing ideas, what are the big problems, challenge problems, and so on. One thing that we can use to make this argument that it is about both exascale and post-exascale is that the platforms that are being stood up, the Frontier, Aurora, the NERSC 9, or whatever the new NERSC machine is called, will be excellent platforms for both simulation and for doing AI training. They'll be okay for inference as well. And we're seeing a huge opportunity in the coupling of machine learning and high-performance computing, and I'll walk you through some of that in a minute. We're also starting to see a different trend, which is, I think, kind of fascinating and fun, which is that historically at the places like the labs and in corporate R&D centers, the people that do modeling and simulation would be people that primarily come out of the theoretical side of whatever the topic area is, right? The people that do theory modeling and simulation. You don't hear about experiment modeling and simulation. But in the AI, when you throw AI into the mix, you now have the ability for experimentalists to be first-class contributors to the ecosystem, okay? Now that does one thing at the labs that should scare the hell out of the supercomputing center people, is that their user base suddenly expands by a factor of 3 in principle, right? And we're already oversubscribed. So the idea that every experimentalist now has a problem that could use large-scale computing changes the landscape, right? Another thing that's going on, in a couple of weeks, there'll be an AI Innovation X Lab Summit. These are DOE meetings around topical areas. The next one is here in Chicago in October. If you're these are invitation-only meetings. But at this point, if you're interested and you're from industry, that's the card you need to get into this thing. Let me know, and we'll get you an invitation. It's downtown at the Drake. It'll be a good venue for this. All right. So what do we mean by AI when we're talking about this in the context of science? So if you were giving a computer science talk years ago, and someone asked about AI, you would show them a chart like this that basically says, on the left, on the leaves of the tree here, are different research areas in AI. Each one of those branches would have had a different way to approach the problem with some kind of handcrafted approach to it, their own community, their own journals, and their own way of doing things. And they were making slow but maybe steady progress. In 2012, something happened that changed all of that. So back in around 2007, at the same time we were launching Exascale, Feifei Li, she was at Princeton at the time, so I had this idea of building a big database of images that had semantic content that was based on a thing called WordNet. So it's about 1 million, well it's actually 14 million pictures, but for the training things that people use in AI, it's about 1 million images, 1,000 categories. And this became a reference database, and it was hand curated. In fact, at the time, in 2012, it was the biggest user of Mechanical Turk at Amazon to hand label these images by people. And so around 2012, there had been this ongoing computer vision contest, which was testing how well the best methods, in the same way that the computational assessment of of protein folding, structure prediction was happening, and the other kind of contest. And every year they got together and they baked off their algorithms. And in 2012, a network, the first time a deep learning system was entered, it was called AlexNet. And it beat, by a long shot, the previous methods, okay? So its introduction of deep learning, 2012, suddenly kind of shocked everybody. And if you go back to your Rolodexes or your calendars before 2012, deep learning was not trending on Google, it was not a thing, really. What happened after that is for every successive years, the traditional machine learning methods were basically nobody did them anymore. And people started doing deep learning, and the networks got deeper. Now they were, all in some sense loosely based on this idea of the neural layering in the human visual cortex. This is, a high-level abstraction. But the effect is that the way we look at AI now is essentially this model, okay? Which is essentially all the problems, natural language problems, speech recognition, speech to text, text to speech, have all been replaced with machine learning, in particular deep learning. You kind of all know this. You should know this, right? And of course, in business, it's taking over as a way to automate things that essentially take about 1 second of thought for a person. Okay? So if you can do something with a second of thought, chances are that AI can do it now and can probably do it better than you can. And things like driving is just like, 1 second after another chained together with don't crash, don't crash, don't crash, how I taught my daughters to drive. And Now, finally, you guys are waking up. All right. So, but you can read, you know, speech recognition is easy to do that way and so on. So that is what's happening kind of in the broader space. Another thing that's happening is a little slightly more technical, which is that why is this deep learning and not just traditional machine learning? And one of the reasons, not the only reason, but deep learning can automatically learn a representation of the data on which it can then do things like classification and so on. Traditional machine learning required a human to construct that representation, okay? The second thing is that as you increase the amount of data, traditional machine learning methods essentially become saturated. And as you keep increasing the data, like you can't read the red line here very easily, but they basically don't get any better after you increase the data. But with deep learning, you can kind of expand the model capacity as you train with more and more data, and so they can absorb essentially that additional data and translate that into improved accuracy. And we see this in our work in applying deep learning to cancer problems with these lines here. I'm going to go through this because I'm giving a higher thing, but you know, you see these blue and orange lines, which are deep learning models, and we hit a point at about 100,000 training samples where they start to exceed the performance of our traditional systems. Another thing that's happening, and this is, I think, critical to kind of get this into your bones. I'm going to try to play this. I don't know, is the audio hooked up to the HDMI? If I hit this, maybe you guys will see this. Apparently not.
A little experiment I made called Bing Translator.
Can you hear this?
Let's see, point your camera at stuff to hear how to say it in a different language.
Bing.
Trophy.
You can't hear this.
Shoe.
Señalización electrónica.
Electronic signage. It's a little hack.
Because I have to keep going.
Machine learning. Cloud vision and translate.
Well, you can see that I can just narrate it where I've done. Just go away. All right. So basically, what this is, okay, this has got two Google APIs. Okay, these are APIs that you can call into the cloud for free. You write front-end code in JavaScript. One of them takes a picture. I mean, you take a picture, you pass this picture to this API, and it attaches an English label to the picture. The second one takes that English language, and you pass it in, and you tell it what target language you want it to be translated to. Okay? So this thing is really interesting. I was sitting in a hotel room in Cardiff last year before a talk, and I decided just to, you know, it was 3 in the morning, as you do when you first arrive in Europe and you don't sleep. So I sat there and I wrote this, but it's only like 14 lines of code. So you write that, and it runs in your browser, and it was pointing at my face, and it says I am 92% forehead, 96% face, and then translate it into Spanish, okay? So the point is that I did this in about 10 minutes with no sleep, okay? Now imagine, maybe I can, okay, all right. See, even the guys at the microphone were asleep, okay? So imagine that this kind of interface becomes possible across many science and engineering and business domains. That is the future, right? 12 lines of crappy JavaScript code running on some server at Google that can do something that you can't do any other way currently, all right? Now, the challenge is, how do we translate that kind of idea into science, okay? So another thing happening, and this is kind of mind-boggling as well, is that the ML community has accelerated in the rate of output. It's not clear it's accelerating the rate of quality of the output, but right now there's about 100 new machine learning papers a day being put up on the archive. You can't read 100 papers a day. It's hard to read 10 papers a day and understand them, right? So this trend is faster than Moore's law, which means that if we don't stop it, the Earth will implode into a black hole of machine learning papers. But it tells you something of how dramatic this shift is, both in computer science and elsewhere. Okay? So what is really possible? We think about this in the context of science. So right now, it's routinely possible to learn a model from a data set which we have no understanding of the mechanistic theory underneath that data set, and to build a model that's pretty accurate, depending on how much data you have and how good the data is, and it works. Okay? And we can do this in chemistry and materials, we can do it in drug design, we can do it in lots of areas. This is a routine thing to do now. Most of the data sets aren't huge, but this is what every undergraduate learns in the first day of a machine learning class. Okay? Your staff can't do that in the first day of their next day at work. You have a problem, competitiveness, right? Second thing we can do is we can learn approximate solutions to inverse problems. Inverse problems are a huge part. I don't know, maybe Earl can say how much of the HPC market are solving inverse problems, but it's a huge fraction, okay? From oil and gas inversion to, Fourier analysis or whatever, we can now use machine learning methods to learn an approximate that will not only solve the problem, where often you can't solve the problem if you try to do it in a discrete fashion, but often much, much faster and with less compute resource. That's mind-blowing. We're using it here for doing phase retrieval and coherent X-ray imaging, but it's starting to be used all over the place. Retrieving molecular structures from MRI data, spectral data, which is something that's a really hard problem, but AI can now do that, okay? The third thing that we can do now is we can use generative adversarial networks, or just more generally generative systems, to learn a distribution of data and then resample those models to generate new synthetic ones. This is what's generating fake faces, fake tweets, fake pictures of Trump and so forth. We can apply it to something that matters, like trying to understand what our physics is telling us about the sky in cosmology, and that's starting to become a huge deal. I have an example there, so I'll quickly do. All right, so it's starting to impact a lot of areas in science. In chemistry, lots of papers. You start seeing things like this, where you input chemical, molecular descriptions, some kind of simple network, trying to predict properties. Kind of works in cancer and drug design. I'm not going to talk about this one, but we can do this in cancer drug response. We not only can do that, we can wrap around it techniques for uncertainty quantification, so we get out predictions that give us a two-dimensional plot. The x-axis down here is how good the drug is, so this way is good drug, bad drug. And this dimension is how confident our models are. And what you discover here is that as we start predicting the best drugs, our models are least confident, which is kind of an interesting thing. Okay? What do we want to do with AI in the future? Well, we'd love to have methods that allow us to integrate symbolic representations of data, like mathematics, all the stuff we have in the textbooks for the last 400 years, with deep learning methods that are coming out of data-centric AI. So in other words, theory kind of AI, symbolic AI with data-based AI. We can't do that yet, which means our AIs are dumb in that they can't read the literature. They can't read physics, they can't read biology, they can't read chemistry and incorporate that knowledge into the models, right? That's done at all if it's done a little bit by people encoding it. So we want to be able to do that. We want to be able to automate and accelerate discovery all the way from planning to execution of thousands or millions of experiments end to end, with the AI both framing the hypothesis and driving the robots, collecting the data, analyzing the data, feeding that back into the models, retraining and continuing to go, and run that at the speed that's possible if you get humans out of the loop. And finally, we want to use AI to advance theory. And this is the hardest problem of all, is trying to devise a way for the AI to read like physics papers and actually to generalize the theory and generate new theories, right? But we think we have a way forward. We see a path. I'm not going to go, or some other things I want to say, but there's too much content here. So we see a map, maybe it will happen in 10 years. Probably the most interesting transformation on this chart is the first bullet. Data, while it's hugely important, is going to be replaced with machine learned models, because the models are way more useful, portable, and securable than data itself. Okay? This will transform everything if we can figure out how to do it, but we're already starting to see it happen. And so in 10 years, for sure, that's going to be a big deal. It's not going to replace data in the sense we won't need data, but what you'll traffic in will be the models, not the data. Okay? Now, what's some opportunities in science? I'm just going to quickly run through these and jump on a couple that matter. So in materials and chemistry, of course, designing things, figuring out how to synthesize things, figuring out how to replace traditional theory with machine learned functions that give us better predictive skill. That's all starting to happen. In materials, we're seeing just hundreds and hundreds of examples of this. In climate, it's a great example of applying machine learning to analyzing global climate models and counting things like severe storms or precipitation events, floods or hurricanes, and doing the things that would require humans to analyze that output data. But machine now can learn to do that automatically. Also to take satellite data and to learn the relationship between what we see on satellites and what is happening on the ground, and then apply that similar thing to climate models. In biology, the applications are enormous. The generalized notion there is being able to predict a phenotype, that is the behavior or the appearance or structural aspects of a biological system from its genome and input from the environment. That we're doing routinely in things like antibiotic resistance. People have been building models that can predict drug-drug interactions, ab initio. Okay? That's related to some work we're doing in cancer. In high-energy physics, there's many applications, too many to talk about, but I'm going to give you one example that is kind of cool. So I mentioned these GANs, these networks that work like a counterfeiter and the police chasing each other, right? So the counterfeiter tries to make better counterfeit money. The police try to make a better detection scheme, okay? And the counterfeiters get better, detection gets better, okay, boom, boom, and they kind of jack each other up. That's a generative adversarial, that's an adversarial network in general. You make this into a generative network, and so you've got a network generating fake examples and one that's discriminating between the fakes and the reals, and it gets really good at doing that. You can apply this to something like generating physics events. Okay, so the guys building detectors at the LHC simulate the crap out of them now on big machines. And of course, they've been doing that for a long time, but every time they do a new detector design, they kind of, you know, oh shit, we got to write another 500,000 lines of code. And they're like, that's really getting boring, right? So the way they want to do it in the future is not to write that code, simply to describe the geometry of the detector and have the machine learning generate essentially all the events that would come from their code. So they've been experimenting with this methodology for doing that. But here's the interesting thing of it. If you look at this chart over here, time to create an electron shower in one of these detectors. If you do a full simulation running on some, you know, Xeon Pentium thing, in this case here it's 17 seconds per shower. Okay? If you take a 3D GAN running on the same hardware, it's 7 milliseconds per shower. Okay? If you run it on something that's actually designed to run these codes, the Xeon's not best at doing that, the GeForce, it's like 0.04 milliseconds. In other words, a speed up factor of 2,500 on a technical computing problem, replacing the traditional simulation with an AI-based generative model. Okay? Now keep that idea in your head, because this is, in fact, not a fluke. We're starting to see it happening more and more, and I'll give you another example in a second. Connecting HPC with AI, there's a lot of things going on here, and it could give a whole talk about any of these bullets, but you know, from steering simulations, we used to talk about computational steering. It meant human in the loop. That's of course stupid. Why would you want to be tethered to your supercomputer for hours at a time when you could be tethered to, you know, Netflix for hours at a time? But you know, steering simulations with AI, that's kind of straightforward, right? You can embed simulation to ML kernels. This sounds a little bit weird, but this blending of machine learned functions and traditional explicit physics-based functions is starting to happen in many areas, and I'll talk more about that. This idea of building a customized computational kernel where the AI is tuning the kernel function to do exactly what you want for the exact context you're in. This is happening by taking molecular mechanics force fields, okay, molecular dynamics force fields, and tuning them using AI to be specific to the target molecule instead of being generic. And when you do that, accuracy improves, speed improves, right? Because you have to have fewer iterations to converge and so forth. We can tune application parameters. We can use generative models like the physics one I'm talking about and comparing to simulations to figure out how much of the science is actually in the model, learned model versus the AI piece and so on. There's a general framework that we're working on here that we call robust learn function accelerators. So basically the idea here is you take a physics code, you make a pass over the code, you identify pure functions that have input-output relationships that you can capture. Every one of those becomes a training set. You run it a bunch of times, it becomes a training data set. You then train a machine learn function to approximate that function, and now at runtime you have the option to swap in the machine learn function. Now what happens when you do that, and you got to wrap some other crap around it to make it robust, like UQ and so forth. But imagine now you have all that, and we've got examples of this. Now when you run that, you have this choice. Do I give up a little bit of accuracy maybe, or maybe no accuracy at all? I'm giving up no accuracy at all, in exchange for the benefits of using the machine learn function, which might be dramatically reduce execution time or reduce power consumption. Okay, so this is now, this idea is, can we automatically transform scientific codes, engineering codes, this way? We think the answer is yes, and we think you capture this uncertainty quantification so you can provide bounds on where the machine learn function approximation actually is robust. Now, people are starting to do this in chemistry, materials. This is an example of trying to apply this idea to machine learning of the Schrodinger equation. So you have a bunch of 2D potentials, some geometry. You have this funky network here. It's a convolutional network that essentially takes these function approximates on these 2D potentials and tries to generate the wave function. And it turns out that you can identify where in the input and the energy space or the input parameters where you get a robust correlation between these two things. And then when you apply this at runtime, you can essentially go from the structure to the computing, say, the energy of some configuration directly with this machine learned model. Now again, like the physics example, the big thing going on here is you get a model that's roughly the same accuracy. This is the showing the correlation, so they're essentially completely correlated in the realm that you're using it, but you get this huge difference, right? 0.3 seconds on a GPU compared to 52 core hours. Okay? So think of this as one use case of AI in HPC are these kind of customizable accelerators that learn from the data in the domain of the application. Now here at Argonne, we've got lots and lots of projects. Each of the DOE labs have 50, 60, 100 projects in AI, which is really machine learning, as I said, right? Applying across domains from 3D printing to cosmology to antimicrobial resistance prediction. It's happening at large scale. There's other interesting things we're applying, of course, in medicine. This example to show you, because it's kind of interesting. One of the problems in traumatic brain injury is we have a lot more CT scanners than we have MRI scanners. So if you fall on the stairs and crack your head, you're most likely to go to a place that only has a CT scanner. But all the diagnostics information on soft tissue injury comes from MRI, right? So we asked the question, can we learn a transformation from the CT images to MRI that would allow us to use the downstream diagnostic tools on MRI? So you train with a bunch of data, there's tons of brain data, right? You use this technique. It's called style transfer in general, but it comes from this idea of having pairs of training data where I like the one with the purse here, right? So you learn to go from a line drawing to a photorealistic image, or you learn to go from, say, black and white to a color picture, or from, say, a aerial photo to a output map or something. So you can learn this essentially ability to transform styles by picking up on non-local correlations in the left-hand image, okay, to come up with the features in the right-hand image. And we said, can we apply this to this transformation of CT to MRI? Okay, so what you got on the left is the real CT image, right? Computerized tomography, axial tomography. It used to be called CAT scans, if you remember, if you're old enough. Remember CAT scans, and now CT, they don't like axial, sounds too technical. To the real MR, which is really a MRI, which is really a nuclear magnetic resonance, but of course people are afraid of the word nuclear, so they drop that. Then they got afraid of the word I for some reason, so they dropped that. So now just MRI, or MR. But anyway, so you've got these pairs, and we learn that style transfer, and then we can generate what we call here the fake MR, okay, fake MRI image, which, naively, if you looked at these two, you couldn't really tell them apart. And the question is, if you run them through the diagnostics programs, do they work? And the answer is yes. And so you could use that generated MRI image, right, to find a tumor, or to find a stroke lesion, or to find a midline shift in a football player, for example. Now, Valerie talked about building an environment for science. one of the things that happens is models become really first-class objects. And not the models that we built HPC, simulations around, but models that we're going to traffic and trade in and so on, right? We have to build an infrastructure for actually finding these things, describing them, publishing them, sharing them, and so on. And this is, sometimes these are called model zoos, is some term, but an infrastructure that makes models a first-class thing that can be trafficked. And models are tiny and relatively easy to move around compared to the terabytes or petabytes of data used to train them, right? So we have a project here called Hubb that's building that. We have another project here called Candle, which is building the infrastructure that sits on top of things like TensorFlow and PyTorch, the deep learning frameworks to make them run on large-scale HPC systems as part of DCP. So it's a Python library and a bunch of glue to make this stuff work. I'm going to skip over that. One of the problems with deep learning is it's great, but it requires too much data, right? In some sense. And there's this, apocryphal kinds of stories saying, well, your 3-year-old doesn't require, a petabyte of data to learn a giraffe, right? You show them a couple pictures of a giraffe, and they, show them another picture of a giraffe, and they know it's a giraffe and not a cat or whatever. Of course, if you say, oh, my 3-year-old child, I want you to be a world expert in recognizing plant species by showing them a leaf, they can't do that problem, right? Too many variations, too many subtle variations. And the question is, what is going on? Is the AI solving the giraffe versus cat problem, sometimes known as the dog versus cat problem, right? Or is it building something that can recognize, species variation in thousands of, say, closely related, plant species, right? But if you assume that we're in the former case, that we need too much data, what can we do about that? Well, one thing that people are doing, this is from a great paper from the Baidu guys, where we're trying to understand the deep relationship between the quantity of data and the accuracy that can be achieved on regression models, and showing that there's a power law relationship there. Now this is good news for the guys that make big computers, because it means that, at least for the short term, until we have a methodological breakthrough, the only way that we're going to get to increased accuracy is with bigger models and more data, right? But if we have that cat-giraffe breakthrough, right, this could change. These relationships could change. And of course, some models are less susceptible to this, in the sense that they learn very slowly with more data. So maybe that's a harder problem. One thing we can do is that we can take trained models and we can dig into those models and we can say, what is the model actually learning? What did the system learn? So this is an example that takes Raman spectra and molecular composition, and it looks kind of like a multi-headed convolutional network here. You train this thing up, and you can look now at the gradients, right, in the variables in that network as a function of the input, and so you get these kind of interesting plots, which may don't mean anything to any of us. But if you're a physicist, in this case a chemist, you can sit down and say, what I'm learning from that picture is some relationship which makes me think of some hypothesis. So this is from an actual study that was done where they came up with about 16 relationships that they discovered from inspecting the internal of the learned model and then conjecturing what was going on from the physics or chemistry standpoint as a hypothesis. So this is really interesting. If we can figure out how to do this automatically, you can take a data set, you can train a model on that data set, then you can hand it off to this model inspector that would look inside that model and say, did you know the following things seem to be holding in relationships with this data, and here's a possible hypothesis that would explain that relationship. This is what I meant by having the machine move us towards helping us with theory, right? I mentioned uncertainty quantification. Can we figure out how to do that? I gave you an example. I'm not going to go through one. Now, how much computing do we need? One of the most important, interesting, press-worthy results of a few years ago was when AlphaGo beat Lee on playing Go. And a few months later, DeepMind trained a model from first tabula rasa with no input data, just on the rules. And that machine, over 40 days, became the universe's best Go player, essentially. And it required about 2 to 3 exaflop days to do that training. Okay? So the biggest groups working on the biggest problems are already doing exascale AI. DeepMind has about 800 people, burns about $600 million a year, of which 180 million of that is paying for computing. So put that into your little kit about the ratio of salaries to computing. Their average salary, fully loaded, is like $550,000. Per capita, they're spending $180,000 on computing. So roughly a third of the same burn on the salary per year per employee. Okay? That's what it's going to take of investment to do first-class AI. It's not cheap, right? This is moving from labor-intensive science to capital-intensive science, right? Of course, Earl asked the question, how many $600 million machines, will there be? This is the $100 trillion question at some level. We know that we can buy at least 3 of them, right? So one of them will be Aurora. It's a great partnership with Intel and Cray. It's going to be a great machine for AI because it has accelerators that are going to be good for training AI. But as is wont, the market is hungry for more price performance in these markets. And so, there's ideas out there for building platforms that can maybe do 10x or 100x better than that. And that's attracting a lot of cash, both in the US and in China, over $4 billion last couple of years in the US, same thing in China. And one question we want to know is which of these platforms are going to be any good for science? Our applications are not the same as figuring out which YouTube videos are cat videos, or figuring out how to make a hair salon appointment that Google's working on, with duplex. You guys know that, right? The duplex. Man, this is really a dead audience. I'm going to have to get my money back. So natural language processing and image processing are the 2 big drivers for the industry. But are any of these platforms going to be good for what we want to do in science? And so there's a lot of places trying to throw architecture at this. It's a kind of, if you're an architect, it's a great day. We've got collaborations with a few of them. A couple weeks ago, you saw this thing pop out of Cerebus, this first trillion transistor chip. It's been a whole wafer, so that if you populate this with, say, 500,000 AI optimized cores, that gives you an idea of what this thing can do if you can do the math. And all the memory is close. It's got 18 gig of SRAM, one clock cycle away from the core. So it's essentially a register. So it's like having your entire model sitting in registers. Put that in, that's just a mind-blowing thing. So one thing that we're trying to do is set up a AI technology testbed. So we did this years ago in the early days of parallel computing. It was called the ACRF, Advanced Computing Research Facility. Rusty Lusk and Jack Langara and I were built that. We're going to do the same thing here for AI testbed. So we're talking to a lot of these startups. We're going to acquire small versions, and if it works, a bigger version. If it works, a bigger version. It'll be opened up to the community, industry, and academic, right? And one last thing we're trying to do. So I mentioned this at the very beginning, this idea of automating science end to end. And one example where we're trying to do this, and it's a partnership with Livermore and GSK, University of California, Oak Ridge, Brookhaven, others. So we're trying to figure out how we compress the drug development cycle from 6 years from idea to first clinical trial, not to market, but to first clinical trial, from 6 years to 1 year. How would you do that? So one way to do it would be to start by building machine learning models that can predict each of the properties we want to know about a drug before we would take it forward into a clinical trial. So we predict things like efficacy, does it work? How toxic is it? How much does it compete with other metabolites? How costly is it to develop, and so on. So imagine you've got a bunch of machine learned models that can predict each of those properties for a molecule. You then drive this system by a generative network at the bottom, okay, that spews out molecules. You learn that by training it on a database of huge molecules. In our case, we have about 3.3 billion molecules that have been, for which we know the structures. And we learn that distribution, then we tell it, go over here and generate 10,000 examples or 1 million examples. We feed those through these top models, which now give us a vector of properties for those drugs, or the hypothetical drugs. We then look at our design criteria. How good does it have to be? How non-toxic and so on. See whether it's in the good region or not. We tweak the search direction. So we loop around this, and think about what this is. This is two machine learning systems, both in inference mode. The first one is running inference generating the compounds. The second array of models is running an inference generating predicting properties. There's no simulation in here, and there's no experiment in this. This runs open loop, it runs closed loop as fast as you can do inference. Okay, so you can search a space of 1 billion molecules if you can manage your search space, in a day, right? Now, you measure with uncertainty quantification how well you're doing. So if you start to wobble, like that chart I showed you where the best drugs had the least certainty, you use active learning to say, where do I have to do some new experiments or some new simulations to reduce the error? Okay, so active learning can do that. We know how to do that with uncertainty sampling. If it can be, if the property we're interested in to improve this can be done by a simulation, we launch simulations. And Dave should recognize that's blue gene, except it's not blue, but it's kind of like Macron yellow vest on a blue gene. It's like blue genes protesting end of life. Anyway, so we do the simulations there. That augments the data set. We retrain, reboot, and keep going. Okay, and in the rare cases where we can't do it with simulation, we launch some experiments. Okay, this turns the whole system upside down. We're not being driven by experiments. We're not even being driven by simulation. We're being driven by purely machine learning inferencing that have been trained on massive databases. Okay, so we're standing this up. It's actually already running. We've got a generic version of this that we're building that could be used for materials, chemistry, and biology. So it has a fast component at the top that generates candidates and tests candidates, does uncertainty and optimization scoring. Then it has a slow mode down here that does simulation experiments. And then we try to make the slow mode go as fast as possible. So how do we do that? Well, simulation, we run it on the fastest, biggest machines, exascale machines. For the experiments, we have to do something different. So we're imagining the following complex, and we're going to prototype this here in the new building in the next couple of years. But it has a AI core right next to the supercomputer, and 6 driver projects ranging from protein to organism design, energy materials, polymers, additive manufacturing, and so on. But when you get to that experiment part, you essentially use massive arrays of robots to do the experiments. And this is there's a couple of companies that are building this out, but Stratios, based in San Jose area, is one of these. But there's a handful of companies. The idea that just like we do clouds for data and compute, we do clouds here for liquid handling robots that can do the biology in the cloud. And so you can get massive parallelism to speed that up. So, in conclusion, we're off to a good start on the AI front. We really have to play it cool by not overhyping this. So any of you guys are thinking about writing an article about what I'm talking about, just tone it down, man. So don't, right? And watch out for the killer robots, because it's basically a race between us and them. Okay? Gosh, you guys are really quiet this morning. Okay, thanks a lot.
So we have a couple of minutes for questions. If you remember what Paul Kearns reminded us last night to have questions to stump Rick. So.
Oh yeah, we'll give that a try. And I apologize to a handful of people that have seen versions of this before, but it was fast. Okay. Well, he's got the mic, and then you're 2 or so. All right, go for it.
I win. So, what do you think the appetite is for risk as we transition over to an AI-based development of ideas and product, when you have especially a federal regime that's based on physical VV&T and a years-long test process?
Well, I think part of the process is educating the federal enterprise that this is happening, and we're doing that. This is like with X-Lab Summits about that, and the DC town halls are about that. But I think the key is to have robust uncertainty quantification. So we want to be able to roll into any scenario where this kind of physical testing regime, classical verification and validation mindset, and say we can tell you very accurately where our model knows what it's doing and where our model has no clue what it's doing. And we can run these models in what we call abstention mode. Okay, how many of you remember taking SAT tests years ago, or have children that take. Okay, so one of the things that you learn in some of these tests is that you get penalized for the wrong answer, and so you're better off actually if you can't narrow it down, not to answer the question. So we can do the same thing in these models. We can say, look, if the error bar is beyond, the error bar in the prediction is beyond this range, don't make a prediction. Say you cannot make the prediction. Okay, so we think that is one way to help manage risk. It will bridge us into this hybrid world where when the AIs can't make a prediction because they don't have enough data, not good enough data, not in the right regime, et cetera, you have to fall back to whatever you were doing before that. Okay? So I think that's one way to do it. There's other approaches, but that's all I'm going to say to that question. You.
Thanks. So scrolling back to like the first couple of slides, 5-year, 10-year, I was beginning to get worried about human attention deficit and network deficits in terms of moving this data and dealing with the output.
That's why models are going to replace data. So we're going to be.
I understand that, but even there, you've got ML papers coming out 100 a day, and who's reading those
tiny
papers?
Yeah.
So.
Well, that's why we have to have the AI that can actually read papers. I'm only quasi-joking. So if you go out and search the archive, you should search for Archive Sanity Preserver. So this is a tool that Andrej Karpathy, who's head of AI at Tesla, wrote when he was at Stanford. And it essentially pre-reads the archive papers based on your reading history and tells you these are the ones you need to pay attention to. So I'm not worried about that part of it. I'm more worried about the, well, I have a lot of things to worry about. But, you know, I don't, first of all, I'm not worried about AI taking over. I'm not worried about it killing jobs. I'm worried about the fact that people aren't understanding what life is really about, which isn't about slaving away at some menial job, right? It's about slaving away at some meaningful job, okay? Like our jobs, right? It was just we convince ourselves they're meaningful. So the AIs, in some sense, will free us up. Plus, it'll be a lot of fun, and the last jobs to be automated will be the ones creating new AIs. So there you go. Any other? No more entertainment is desired for this morning?
You said that at the beginning, when we talk about...
I've seen you again, Thomas.
we talk about AI today, it's really deep neural networks.
Is what?
Deep neural networks.
Mostly. I mean, not entirely. I mean, you know, we've got reinforcement learning. We have
when
other
you
things.
say you need to throw the data away and you just keep the models, what you mean is you have you know, I'm not debating this. You have an extremely good way of compressing the, you know, the data and getting the relevant information out. But isn't that a bit a dangerous way of characterizing AI, basically bringing it down to just compression of data and nothing more?
No, I'm not saying that at all. I'm saying that all I'm saying is one of the side effects of getting really good.
Sorry to horn in.
No, it's no problem. Exactly. I mean, one of the side effects of pursuing this AI agenda, okay, is that we will get really good at learning what is learnable out of data, and it won't be necessary if we desire. We can keep data as long as we want. I'm not saying throw away your data. I'm saying that it will become possible and therefore really interesting, right?
I totally agree with this point, that this is an incredibly good compression and a mathematical tool to understand, analyze data. I have no issue with that. But that's not artificial intelligence. It's a tool.
You have more than that going on up here? That's a beer discussion. But, I mean, so I said a lot more than that,
well, you
Thomas.
said
So you're picking on one bullet.
Good things that we are good at, and by the way, looking at massive amounts of data, we are not good at that at all. We're not good at solving very large sets of equations either.
Absolutely. So what I was trying to argue for, okay, is that, and first of all, you picked one bullet out of 1,000, but you can do whatever you like. That, I'm not advocating that in the short term, some kind of artificial general intelligence, some immortal companion is going to emerge from the silicon slime and be my partner in crime, right? Nobody knows how to do that, right? What I'm talking about is in the next few years, the next 10 years, we can see a pretty clear path for how AI, as I'm describing it, a lot of deep learning, other techniques as well, merging and hybridizing with traditional HPC to give us a much more powerful suite of tools to attack problems in science. And the rest of the conversation I'm happy to have over drinks because it's philosophical at some level, right? It's going to transform the rest of our lives. You know, self-driving cars and self-flying airplanes and self-driving labs and self-fitting shoes or whatever you want. I'm not advocating or not advocating for all of that. That's all going to happen. But in science and engineering, I think this is a pretty broad view of what is possible if we decide to pursue it. Now, other things might be also possible. I'm not saying that's not true. I'm just saying this is what I can see at the moment. So, you owe me some wine.
Good. All right. Let's.
Cheers. All right.